Hi everyone, welcome to the first CSP seminar this semester. My name is Qing and I'm a assistant professor in ECE. I'm the main organizer of this CSP seminar. Because the starting of semester is a bit hectic, so I volunteered to give the first seminar. And this talk is about some very recent work I'm working on. I find quite interesting. Some of the work is kind of preliminary, but I want to share with you. So the basic message I want to convey is that when you're training the deep neural networks, actually there are some low-dimensional subspaces, especially when your data have certain low-dimensional structures. And by leveraging this kind of invariant subspace in your training, there you can achieve two things. One is that you can achieve training efficiency. You can do low-rank training to accelerate your training efficiency and also compress your network. The second message I want to convey from this talk is that if you understand this kind of training structure, you can understand the representation structures inside of the learned neural network. So I made the slides in the last minute. So if there's something wrong, just bear with me. And to start this talk, I want to start with a classification problem, like multi-class classification problem. So we all know that deep learning has been very successful in the past decade, but we want to look deeper to understand what is going on. And here we just take an example of this multi-class classification, and we consider the problem in the super setting, right? So we have a bunch of label training data sets where X could be our images and Y are our labels. And we consider the Y could be one hot label, right? So, and we consider, for example, Amnis data set, it can have 10 class. And the one hot label is just, say if the input image X is a cat and belongs to the first category, then move the mouse. Then the one hot label is basically a primitive vector that assigning the first entry to 1 and all the other entries equal to 0. And for the majority of the talk, we'll consider the training data set is balanced, where each class have the same number of training samples. And to train a neural network for classification, right? So we just let's consider a vanilla multi-layer perceptual network. So X is our input, and multi-layer perceptual network is basically each layer you are doing a linear transformation by a weight matrix followed by certain nonlinear activations. And upon the last layer, you use a linear classifier WL to make the decision, the prediction. And here for the notations, we are trying to understand the feature structures in each layer. And here we use ZL to denote the output feature of specific layers. And intuitively, what I believe is that the neural network is basically progressively doing linear separation. Although the input data could be not linearly separable, but by using this kind of a nonlinear transformation of your data in each layer, so what each layer is doing is that it's doing a linear separation of your data. So upon the last layer, the features are linearly separable. So actually, we can numerically verify this using some simulations. So here, what I want to show you is that we did some I think I find this quite interesting, but actually this result had been previously reported in other papers as well. Here, what we do is that we train a 10-layer nonlinear multi-layer perceptual network, just like what we showed here. This is a very simple network on the CIFAR10 dataset. And here, what I'm showing here, so this dashed line is showing the rank, the numerical rank of the output feature on Z, where we concatenate the Z of each layer as a matrix, and we calculate the numerical rank. And the blue line is showing the classification accuracy of each layer. What we are showing this line is that for each output of the layer, we are doing a linear probing on that particular layer and report the training accuracy. And what you can see from this figure, where the x-axis is the number of layers, and the thing on the left, y-axis is reporting the numerical rank, and the right y-axis is about the training accuracy, reporting the training accuracy. So what you can see is that when we see from the shallow to deeper layers, what you can see is that the rank of your features actually is progressively decaying. And the training accuracy, if we do linear probing on each layer, you can see that the training accuracy is already achieving a pretty high accuracy if you do a linear probing on that some very like on the third layer, right? And the increase of the training accuracy is marginal in the later layers. So which means that in the early layers, you already linearly making your data quite linearly separable, and in the final layers, in the initial layers, you are making the data more and more linearly separable. And what the network is doing in the final deeper layers is compressing your features to the means, right? So that's why they are making the rank of the features pretty low. And we also introduced some different metric, right? So numerical rank is one way to measure the feature compression, and the accuracy, the training accuracy is another way to is one way to measure the linear separability. But actually, you can introduce some exact metric to measure the feature separation and compression. I will talk about this concrete definition of feature separation and compression later on in this talk. But suppose we have some like a metric of measuring feature separation and feature compression, and if you just utilize this two metric, you just assume that you have two metric, and you measure this separation, the compression across layers, what you can see is that the separation is indeed increasing across layers, which means that the features are more and more linearly separable across the layers. And the compression means that the features, right, so it's compressed, especially in the later layers, right? So it's extremely compressed in the later layers. So here what I mean compressed is that the features actually concentrating to the means of the features in each class, right? Yes?
The separation is in terms of the feature mean, right?
Yes, in terms of feature mean. Say you have 10 classes, and the rank should be probably around 10. So the main message is that actually in practical neural networks, right? This is what we are doing on MLP, but actually if you do on like a ResNet, vision transformers, all that kind of a network, practical network, you can observe similar phenomena. So actually this feature, there's a progressive feature compression and a linear separation from shallow to deeper layers. And if you visualize the features, do a t-SNE plot of the features, right? You can see that the features indeed are becoming more and more linearly separable. Yes.
So there's some networks like autoencoders that are intentionally designed to compress features. When the network sort of learns to do that automatically in like a feed-forward network, does it learn? Do you know if it learns like a similar method of compression as like when you explicitly perform compression in an autoencoder, or is it like a fundamentally like different kind of compression?
I think maybe it's different. So you are asking auto encoder is a regression problem. Here we are like talking about word. Yeah, maybe I'm not exactly sure actually. So there are, I mean, from this experiment, actually there's something further implications of this. So one thing that you noticed is that, so in the deeper layers, right? So the features are extremely compressed. So you may ask why the features are like extremely compressed in the deeper layers. And we look at the training phenomenon of the nonlinear neural network, and you find something very interesting is that, so here what we plot is that we are plotting the gradient learning dynamics of the final layers of some neural networks, like deep linear networks, multi-layer perceptual networks, toy VIT, and some other variants of VIT vision transformer models. And what I'm plotting is plotting for VIT is the MLP layers. And what you find is that actually you plot where the x-axis of each is plot is the singular values and is sorted. And the y, this y-axis is the learning iterations. So here is from the 0 iteration to like say 20 epochs. And the this z amplitude is showing how large the singular value is. And you can see that, so there's a very obvious low rank structures in the weight matrices in the last layer. And this one is for linear network, and this is for MLP, right? And you can see that actually this learning is exactly happening near invariant low dimensional subspaces for the weights. And that's why there's a lot of work that arguing that it's low rank, the neural network are learning low rank embeddings, and because the weights are low rank, and it's actually promoting this kind of low rank structures in the representations. And in the later part of this talk, we will try to investigate why this is happening in training, like some idealized neural network architectures that actually we can rigorously prove that when you're training the weights, actually the weights, the update of the weights is only happening in an invariant low rank subspace.
Okay. Is this a constant width MLP? Maybe in the previous example of that simulation, what's the width of your? It's 10 layers, but how wide is each layer?
I'm not even sure. I need to ask my students about this.
Okay.
Yeah.
I mean, it must be constant width because you're comparing, right? And you don't. I assume that width is wider than the input data. Like there's
right.
lifting. Yeah. Okay.
And here the rank actually, the dimension of the subspace actually is like is equal to the number of classes, or two sides of the number of classes. And this is measured in the final several layers. Yeah. As you can see that from this figure, right? So the features are compressed in the final layers, right? So you can imagine there's a low rank structure happening there. And actually, when you're training the network, the low rankness, the rank of the weights actually is not changed. And the updates is only happening in invariant subspace. So the second thing is that thing that we investigate based on this phenomenon is that you can see is that the features are already linear separable at the initial several layers, right? So you might question, right? So if we replace the deeper layers by a linear network, what will happen, right? So we use a hybrid network where the first several layers are nonlinear network, and we just replace the later layers with linear network. What will happen? And we did this. So we used like a 10-layer hybrid network, where the first 4 layers is MLP, and the last 6 layers are just a linear network without any nonlinear activations. And you can see that actually the trend is very similar to nonlinear network, right? So the nonlinear network in the initial layers is basically making your feature more and more linearly separable. And so in the deeper layers, so even if replaced with a linear network, you are achieving pretty high training accuracy, which is 100 on CIFAR data set. And the numerical rank, right, is the linear network is also acting as a feature compression. It compresses your features to lower dimensions, right? And the right-hand side is about linear separation, right? So it's about separation and compression. We use the metric we introduced, and similar things happened as shown on the 10-layer MLP network.
Sorry, Qing, I have to ask. So 6-layer linear is equivalent to 1-layer linear, right?
Yeah, that's right.
What's the point of
But the linear network is over parameterized, right? So you have a more parameters in the linear network.
So now it depends on our training algorithm.
Right.
So what local minimum or whatever. Okay.
So there is no linear activation.
No nonlinear activation. And what you can observe for this hybrid network, you can see that actually you see similar phenomena, right? The features are linear separable and they are compressed in the across the layers of the network. So this motivates us, like maybe to study the phenomena in nonlinear network. Maybe the first step is to look at the training in deep linear networks. Sorry. Okay. So a deep linear network, as Jeff mentioned, is just like a linear transformation of your data, right? So here if we consider a L-layer deep linear network, you just remove all the nonlinear activations between them, and this is essentially just a linear transformation of the data. And actually, in practice, people, I mean, in the past, there's a lot of people like using this deep linear network as a prototype of studying nonlinear counterparts. That actually there's quite a few similarities between linear and deep linear nonlinear network. So one similarity, as we showed here, is that there's a similar linear separability in the deeper layers, right? So we see that if we do a hybrid network, then actually the linear part is just to do compression of your features. Once you're in the initial layers, you make the features linear separable. So secondly, is that the linear network have similar compression of your features in the deeper layers. And also another thing as we observed is that for deep linear network, the way it's also process similar low rank structures. There's a recent work on studying the low rank representations embeddings of linear and nonlinear networks. They observe similar phenomena. And the training of a deep linear network actually could be non-trivial because the network, if you look at the loss function, actually the landscape could be highly non-convex. It can have many saddle points. And also if you consider linear network, it can be, I mean, because we have many layers, it can be highly over-parameterized, then potentially have even many local solutions that they are not global solutions, right? So we would prefer certain, there are many existing work showing that the gradient descent have certain implicit bias towards low-rank solutions. And because of the loss is non-convex, the gradient descent dynamics could be highly nonlinear. So there's quite a few challenges, even we study this deeper linear network. So in this talk, we will study some of the interesting phenomena I showed here based on deep linear network. And we show something kind of interesting is that, so even you just look at this deeper linear network, and if you just look at the weights of the neural network, we find that when your data y and x has some low dimensional structures, actually the training, the weights update is only happening in an invariant low dimensional subspace. And by using this kind of low dimensional subspace structure, we can do several things. One is that you can do network compression. You can compress your network and do much more efficient training. And so this low rank training and network compression actually is not only happening on deep linear network. Actually, we can demonstrate some promising directions on low rank training and compression on nonlinear networks. So another thing is to understand the hierarchical representations of deep neural networks. And so as we showed previously, right, so the network is like progressively compressing and separating our features, right? And actually based on deep linear network, if you study the deep linear network on linearly separable data, you can show a similar result that actually the network, each layer is basically doing linear feature compression and feature separation. So that's the main message I want to convey here. So for the rest of the talk, first I will introduce this kind of invariant subspace structure of the gradient dynamics for training deep linear networks. Then I will discuss about low rank training and network compression. And finally, I will talk about how can we utilize this result to understand the hierarchical representations of training neural networks. So before that, any questions? Okay, so no questions. Yes.
In the last three before, you said you conclude three similarities at the deep linear network, which has the similarity performance with nonlinears.
So it's not. I mean, this is it's overclaim. So I want to say is that the linear network is only like mimicked nonlinear in the deeper layers because the feature there is already linearly separable, right? So if you replace with a linear network, you can do basically the last several layers is doing like feature compression. A linear network can still do feature compression in the last several layers. But I agree that this, study deep linear network cannot like fully, just a prototype of studying nonlinear network. There's still like huge gap there.
And can you turn to the next page? Next page. Yes, the similarity here.
Yes.
So does it conclude dataset Silverton, or are there any other dataset tested to conclude those similarities?
So the similarity of linear separability is that the initial several layers of the nonlinear network is already make the data separable, linear separable, right? So if you replace that with a linear network, the later layers basically doing feature compression.
So you tested?
Yes. The experiment result is showing that here, right? So if you look at these figures.
Oh yeah, that means this is on the CFR10 data set.
Right.
Have you test any other data sets?
No, but there's some existing work that showing this, but we only do this experiment on the CFR data set. It's not exhaustive. Yes.
So this is for like a 10-layer network. If you make the network deeper, does it become lower rank or does it just stretch and process out?
It also depends on your initialization, actually. The initialization scale of your gradient descent. If what we can see is that if your initialization scale is small, then actually your feature will be more compressed. And also, of course, you make your like network deeper, but deeper network is harder to train. Yes.
And just to follow that, you mean the initialization is on the weights parameter, right?
Yeah.
And the compression you mean is on the feature embedding.
Right.
Yeah, so which means that if you have a smaller scale for the initialization on the weight, then the beginning stage of the features will be more linear separable.
It will be more compressed, I think, the initialization. Yeah.
I see. Yeah.
Question.
Yes.
Did you try this on convolutional networks?
No, we haven't, because convolution networks, the convolution is a circular matrix. Actually, it's very hard. If you reshape the convolution matrix, not exactly this matrix, right? I think this is something that promising to study the MLP layers in the vision transformers. There is just a fully connected matrices. So let me introduce the result. So here we are starting, like a deep linear network. So X is input, Y is our labels. And as I mentioned, we are training a deep linear network by minimizing some loss, least square, just the least squares loss. And what we do is that we use a epsilon scale orthogonal initialization of the weights. And we studied the learning dynamics of gradient descent starting from this orthogonal initialization. Where this lambda here is the weight decay, is controlling how much weight decay you're adding to your weights. And here we make some further assumptions. We actually assume the weights are a square for each layer, and we assume the inputs are whitened, but actually this can be relaxed to near orthogonal weights. And we also assume that actually this cross correlation matrix Y multiply X transpose is low rank. And the low rankness is kind of like a natural, because if you consider a classification problem, right? So this Y is a one hot embedding matrix, and this one hot embedding matrix could be just a very low rank matrix. And later on, we will also consider some like a matrix, low rank matrix completion, and this matrix X could be low rank. So if you consider this correlation matrix, it could be a low rank matrix. And when you consider this problem under this setting, actually we can show that when you train your gradient network through gradient descent, then the weights actually have some very nice invariant low rank subspace structures. So here is an illustration. So we train a 3-layer deep linear network with squared weights, and the rank, say we have a 3-class classification problem where the rank of Y, the one hot embedding, is equal to 3. And if you look at, so this is a plot of the last layer weights of the deep linear network. So for example, deep linear has 3 layers. We are plotting W3, the singular value decomposition of the W3. Oh, sorry, this is W1. This is the first layer. My mistake. So here again, the x-axis is showing you the sorted singular values. So x-axis denote the index of singular values, and the y-axis is showing you the number of iterations, and z-axis is showing you the size of the singular values. And what you can see is that actually the training is exactly happening in like a dimensional, 6-dimension subspace. Here, and actually this subspace is invariant across all the training iterations, right? So it's only happening with like a 2R subspace. And here, the dominant singular values in the first 3 index, and actually there's the other 3 singular values are changing in the later part. If you combine those 2 parts together, right? So this is like a 2R invariant subspace. Actually, the training for the rest of the singular values is totally unchanged through the whole training process. And this is about the singular values. So how about the singular vectors? So if you look at the singular vectors, right? So what we are measuring here, we are in the middle figure, we are measuring the correlation, the inner product between the singular, the left singular vectors with the initialization. So basically we are measuring something like this. So we track the changiness of the singular vectors, and you can see that the singular vectors is also only changing in the subspace. The rest of the singular vectors are not changing. And similar things is for the right singular vectors, that they are also changing only within invariant low-dimensional subspace. And you can do, and this is what we are showed in the first layer, right? So and actually you plot the changiness across all the layers, like layer 2 and layer 3. You can see similar things happens, right? So the training is only happening within invariant low-dimensional subspace. and the rest of the singular value, the subspace are not totally unchanged. And this is some simulation, but actually you can rigorously prove this. So what we can show is that when you're training like L-layer deep linear networks, and it's supposed that the cross correlation matrix is rank R, and you can show that actually there exist some orthogonal matrices, and actually you can decompose your weights in the following form, where the both left and right singular vector, the singular matrices are totally unchanged. There's only like a 2R by 2R weight matrix that are changing. And the rest of the singular values, they are controlled by something like a row. They are totally identical. And this row actually is critically depending, essentially depending on the initialization of your weights. So you can imagine this row actually something relates to the initialization scale like epsilon. So you can just think of the row is equal to something dependent on epsilon. If epsilon is small, then actually this the rest of singular values could be pretty small. And you can consider another case, but essentially you can show similar things. So because here we consider two cases, is one, the first case we'll utilize this for matrix completion, and the second case we'll utilize this for classification problems, understanding the representation structures in classification.
So what is F?
M. So M is this dx minus 2r. So you can, this is just the rest of the weights, the space.
And W tilde of T starts as an identity. Does it stay diagonal or does it?
Oh, it doesn't stay diagonal. It will be like it will be updated.
And the updates affect all of its elements.
Right, right. So if you look at this figure, right, so the eigenvectors are changing in that W tilde, and actually it's essentially it's changing there. So yeah, to further address Jeff's question, right? So if you write this W tilde as like a singular value decomposition, right, you can see that actually the left singular vectors, left singular subspace is changing, and the singular values in a small subspace is changing, and the right, like a very small subspace is changing, and for the rest of the subspace is totally unchanged. It will just stay there throughout the training process. So this comes to our the second claim of an implication of our theorem is that so actually the majority of the subspace actually is unchanged, right? If you have some low dimensional substructures in our data, either in the label or in our input. And the learning process actually is only happening with 2R dimensional invariant subspace. And also our results can shed light on some recent work that they are claiming that deep network are learning low rank embedding, right? And the reason for low rank embedding is that if you say use a very small initialization, so you make your epsilon very small, right? So say if you make your epsilon initialization very small, then what this means is that these singular values actually for row is very small. And then the way to learn actually is low rank. That's why you are learning low rank embeddings in your when you are using gradient descent to learn the parameters of your network architecture. And actually, this invariant subspace actually here we approved it under quite strong assumptions where our input is whitened. But actually, if you like say utilizing, actually in experiment, this phenomenon happens more generically. So see if your input data are not whitened, but some like near orthogonal data, you can see that this invariant subspace is also proximally holding. And this kind of invariant subspace is also holding not only for gradient descent, but also but holding for variance of gradient descent. Say if you inject momentums, like some Adam type algorithm, and you plot the weights, the changes of the weights, you can see that this update is also happening in an invariant subspace of the weight parameters, weight matrices. And next, I want to utilize this phenomenon to show you that how useful this result could be. I want to show you two results. I'm not sure I have enough time, but one result I want to show is that if you know that your weights update in a low rank subspace, right? You can do efficient low rank training and network compression. You can train your network much more efficiently. So in the second part, I will talk about this. And we call this phenomenon, we call this phenomenon law of parsimony in the gradient descent, but actually, in the rebuttal, the reviewer don't like this name. So I think it's a little bit, the law is a little bit like more universal. So the main message I want to convey in the second part is that if you know that the training is happening in invariant low-dimensional subspace, then what you can do is that you can do efficient training, right? You can just update your weights in such a very small subspace, and you can achieve much more efficiency. And this is what we can show, right? So we do this for a problem called deep matrix factorization, deep matrix completion. And you can see that by using this idea that the training only happening in a invariant low-dimensional subspace, you can achieve the same training trajectory with original training, but your training will be much more efficient. So this blue curve is the original training method, and if you do a low-rank training, actually you will be much more efficient, but you can achieve the similar performance compared to the original approach. So the problem we considered here is a problem like called deep matrix completion. And the basic problem is that, say, if you want to recover a D by D matrix, but you only have a partial observation of the matrix. And what you want to do is that you want to, say, use a 3-layer network to approximate the underlying low-rank matrix phi. And here, if the omega is the index matrix, it's just indexing what observations you have. So if omega is a R1 matrix, right? So this simplifies to deep matrix factorization, which is a toy problem. And if L, the layer is equal to 2, right? This reduces to Barreau-Montero factorization type of formulation. And recently there's some work showing that if you increase the depth of the network, say you increase L equal to 3, actually deep matrix factorization have some benefits over the Barreau-Montero type approach, especially in the over-parameterized regime. So here is, we can show that actually both increasing depth and the width have some benefits. So here in the over-parameterized regime, where the underlying rank of the matrix is unknown, if you increase the depth and you compare a 3-layer network versus 2-layer network, and you overestimate the rank, you can see that when you do rank overestimation, the 2-layer network will overfit when you increase the width of the network. But the deeper layer network, the 3-layer network, will not overfit. Another thing is that for a deeper network, if you increase the width, actually the width is doing something like a preconditioning that they will reduce the number of iterations. It will accelerate your convergence. However, increasing the depth of the width will significantly adding to the number of parameters that you use. So the over-parameterization is a double-edged sword, right? So it, on one hand, it improves sample complexity, improve your performance in over-parameterized, like a rank over estimation regime, but it will slow down the computation per iteration. right? So the question is whether we can achieve the best of two worlds. We can achieve faster convergence, but we also achieve the similar performance with like over-parameterized deep linear network. So actually we can do this by using this kind of idea of invariant subspace idea that I showed, that the training is only happening in an invariant low-dimensional subspace. And to motivate how can we achieve this, let's consider a toy problem where this deep matrix factorization. We just consider that we have a full observation to all the indices, and give some intuition how can we do like efficient optimization for deep linear, like deep matrix completion. So as a starting point, let's just consider this deep matrix factorization. And so by the lower parsimony, if you consider the gradient descent, running gradient descent on the weight from a small epsilon scale initialization, because like in our theory, we can show that different layers of U and V, actually they are orthogonal to each other. They can be canceled. Then you can write this end-to-end matrix, something in this form. And this is because the cancellation of U and V cross layers. And you can actually write your end-to-end deep linear network, something in this form. And if you buy this lower parsimony, right, you can expand this, and you can write this as summation of the first part, which is about the compressed the subspace, plus the rest of the subspaces. And here the key is that if your initialization is small, you use a very small initialization, right? So the second part actually is very small, because you are power to the L, right? So it could be very small. And if you get rid of, you just ignore this residual part because you are using a very small initialization, then the weight is approximately equal to the compressed weights. And then essentially when you update the weights, you are just updating the weights in like a small subspace. And the claim is that if you, when you're running gradient descent on the original weights, it's almost equivalent to running the gradient descent on the compressed weight parameters. And by doing this, actually, if you run the original gradient descent on the original network, right? So the number of parameters you need to optimize is L multiplied D squared. But the compressed network, actually, the number of parameters will be L multiplied R hat, where R hat is the overestimation of the rank. And you can see that you can achieve the training trajectory is exactly the same with original network, but your training speed will be significantly accelerated. However, this is for deep matrix factorization, right? So how can we extend this approach to completion? So if you run this approach exactly as we did for matrix factorization to completion, actually not working very well. So this is this blue curve, green curve. Orange curve is the compressed network trajectory, and it diverges from the blue one, right? And you can see the arrow stackness here. And this is because if you consider this omega, this index matrix with the low rank matrix, and this is not exactly low rank. So what we do to counter the effect is that we in the deep matrix factorization, we don't update the UL, the U and V, the small like singular vectors on the left and right. So to sorry, I think there's a remedy for the matrix completion is that we use a like a different learning rate to slowly update the U and the V on the left and right. And by doing this, if you look at the dash curve, right, you can achieve like similar performance with the original network by updating the U and V on the left and right. And doing that, you only pay a little bit of about extra complexity, but you can still achieve pretty fast convergence compared to the original deep matrix factorization approach. Any questions?
Is it the empirical result that you test what is the optimal learning rate for UN?
Yes, you need to tune a little bit, but the update will on U and V will be slower and the updating on this W tutor. Yeah.
And this is just for the linear things that.
Right. So next slide, I will talk some ideas of extending this to nonlinear networks. So for nonlinear networks, I mean, if we look at what I showed in the initial slides, right? So we showed that the low rank invariant subspace is also happening in the deeper layers of the nonlinear network. So if we go back to several slides from the beginning, so if you look at this plot, you can see that actually the invariant subspace is happening in the last several layers of a nonlinear network, right? So there's an invariant subspace in the last layer of MLP, the MLP layers of the vision transformers. So we think that maybe we can do low rank training in the last like 2 or 3 layers of this kind of a nonlinear networks, because the data there is already linearly separable, right? You can there could be some strong low rank structures in the nonlinear networks in the last several layers. We did some initial investigation on this. So the result is not very complete. So the idea is that in the last, like say, 1, 2, 3 layers, we do low rank training of nonlinear network, and the rank we choose should be like strongly correlated to the class number. I mean, we can choose a rank of this low rank factorization based on the number of the classes. And by doing this, right, we can significantly reduce the number of parameters and improve the efficiency of the training. We did some initial investigation of 3-layer MLP networks, and actually we did some low rank training on MNIST. So we can see that actually we can save some of the parameters. And we drop some like performance, but the drop of performance is not that significant. But still, we need to do more investigation of this, and we believe this can potentially be applied to vision transformers. We can apply this kind of low rank training to vision transformers of the last several layers. So another thing is that this invariant subspace actually might shed some light on recent work on LoRa. So LoRa is a low rank adaptation approach, right? So see if you pre-train a large scale model, and then you want to fine tune your model on downstream tasks. So usually what people do nowadays, they use this kind of low rank adaptation, like parameter efficient fine tuning methods called low rank adaptation or LoRa. So what they do is that this W0 is the initial weight of the pre-trained model, and then you add a low rank components. You only fine tune those low rank components, and you will see that actually this is a very popular approach in large language model. Actually, achieve pretty good performance. And if you just see the illustration here, right? You have full model. In the LoRa, the number of parameters actually is significantly smaller, but the performance would be like not that different from full model fine tuning. And I think this the theory we proved here might shed some light, give some insights on why this kind of LoRa low rank adaptation works in practice, because the update actually is only happening in invariant subspace, right? That's why you can do this kind of a low rank factorization using LoRa.
For the number of parameters, you have 2 values. What's the, in the column called number of parameters, you have like 0.33 millions divided by or /86 point. What are the 2 numbers there?
I think this is 233 is the number of parameters you fine tune. and the right is the whole number of parameters.
So you still have to store in memory or in your GPU all of the parameters, but the learning part is the part you're adjusting is still.
Right.
Okay. There's not really compression in that sense.
Right, the fine tuning is not a compression, but the low rank training is definitely a
Yeah,
big compression. Yeah.
My question might be a bit off topic, but I mean, like, why is it just happening from fine tuning stage, not in the pre-training stage? Can we just
I think for a large language model, you have many number of classes, right? If you have too many classes, also our theory indicates is that the compression is the rank should be like proportional to the number of classes. I think that's maybe there's a reason that you cannot do low rank training for a large language model because there's too many classes. But I think for classification, like vision problems, if you even consider ImageNet, right? ImageNet have some like coarse classes, like they have some tree structure classes, right? Maybe there could be still some low rank structures, even you have like 1,000 number of classes, because there's some larger classes. So the larger classes could be like a 3 or 4, something like that. There could be still some strong low rank structures there. Yes.
If this is going beyond like the classification problem, you think this kind of low rank property can still be perceived? Because, for example, like when we are using LoRa for fine-tuning large function modeling, and like when we are doing for like image caption loss, so your output is something like to predict the next tokens of the word, right? Yeah, so it may not have like the category-based semantics that can get from the supervision.
Right.
But do you think in this kind of like other loss function supervision, this kind of the conclusion that we can see from the classification-based problem can still be something share the same insights or?
That I don't know. Maybe we can talk offline about this. I no clue about this.
Yeah.
Sorry. So I don't know. I don't have enough time. Maybe I'll just go quickly about the third part. And the third part actually can utilize this kind of idea to study the, as I mentioned at the beginning of this talk, right? So network is basically doing feature compression and separation. And actually you can utilize this kind of idea to explain why the network each layer is doing progressive separation and compression. So what we showed actually is that by utilizing this idea, you can show that the deep linear network actually mimics the nonlinear network in terms of feature compression and separation. So as a setup, we consider a classification problem, right? So we training a balanced data set. We consider, we write a feature Z as intermediate features, right? For each layer, for else layer. And we introduce the notation of, to introduce the notion of feature compression and feature separation. We first define the within class and between class covariance matrices. And the W, sigma W is within class covariance matrix, and the sigma B is the between class covariance matrix. And we define feature compression is like this. So we take the trace of the within class covariance matrix divided by the trace of the between class covariance matrix. So you can see the key factor is the trace of the within class covariance matrix, right? So if you take the trace, it's basically measuring how close each individual sample, sorry, here should be an extra L here. It's basically measuring how close your individual feature to the class means, right? And it's a trace of the between class covariance vector. You can think of as like a normalization factor because you want to get the scaling effect. And we measure the between class separation based on the feature means. So here, UL is basically measuring the feature mean of individual class to the global mean. So the distance from each class to the global mean. And you measure, sorry, here should be 1 minus this thing. So here should be 1 minus maximum. And it's basically measuring how separated of the class means to each other. And if you have an actual 1 minus here, right, you can imagine this one, SL is larger, then actually the features are more separated. And when DL is smaller, the features are more compressed. And we evaluate this DL and SL measure on both linear network and nonlinear network. You can see that the feature compression, right, is happening with a linear decay ratio from shallow to deeper layers. And for nonlinear network, this feature compression is also happening almost like a linear decay ratio. So the upper one is this linear network, and the bottom one is nonlinear network. And so, and this figure is showing you the feature like a separation. And you can see that actually this feature separation. So am I using the right slide? Sorry, I think I'm using the wrong slide. Sorry, wait a second. Let's bear with me a little bit. It's not updated. Somehow there's some mistake. In other way, so you can see that actually this is measuring the feature compression. This is feature separation, and you can see that actually this separation is increasing from shallow to deeper layers. And to show this, actually, I mean, so this is some old slides. I'm not sure whether there's something wrong here, but basically, what you can show is that you can show this result based on this law of parsimony, that the training only happens within an invariant low-dimensional subspace. Is that actually you because there's I mean, we can show that when the training converges, right, the spectrum of your network actually is only like changing in like a small subspace, such that actually the singular values of each layer is around epsilon, and that's why, because the singular values of each layer is around epsilon, is like a compressing the features across layer using a epsilon level of scaling. And we also did some interesting like experiment to showing that actually this initialization scale actually is affecting the compression ratio, right? So you can see that on linear network, if you use a larger initialization, right, the compression of your features is happening slower when you're using a smaller initialization, right? So if you use a smaller initialization, then the feature compression will be with a faster ratio. Oops. However, there's a trade-off between initialization and feature compression. If you use a small initialization, you will be more closer to the origin, right? So the origin will be a settle point, and the skipping settle points will be taking more iterations. So if you use a larger epsilon, then the feature compression will be happening slower, but your training will be faster. And if you use a smaller epsilon, then your training will be slower because you will need many iterations to skip settle points. But in return, you will have a faster compression across layers of your neural network. Yeah, so I think there's some mistake in my, slides are not updated somehow. So there's some issues. So with that, I want to conclude this talk. So in this talk, what we showed is that the gradient gradient descent learning process only actually we look at the neural network training with gradient descent. So what we showed that for deep linear network, the gradient descent only happening within an invariant subspace of each weight matrices, and actually the remaining single values are staying affected through training. And by leveraging this idea, actually you can do a lot of things. I think the majority of two things. One is that you can do efficient low rank training and network compression. And it could potentially share light on some like a LoRa type of methods. And secondly, we can utilize this idea that the chaining is only happening in invariant subspace to understand why the network is hierarchically doing network feature compression and the separation across layers. Thank you. I will take any questions. Yes.
Hi, Qing. Thank you for your talk. It's really impressive. I just have one question for this low minimum invariant subspace. So I'm wondering for the generalization of neural network to different domains, is this can this invariant subspace help? For example, we use this subspace for different domain for domain adaptation or some similar stuff.
I see. So you are talking about the domain adaptation. I think this for domain adaptation, I think learning low rank features might not be a good idea because it's eventually leading to the feature collapse, neural collapse. And there's a lot of argument that if your feature collapse, actually the domain adaptation that also distribution robustness will be bad. Actually, I think we need some new ideas to prevent feature collapse there.
Thank you.
Maybe I'll take Clay's question first.
Okay. I'm just curious if this low dimensional structure could possibly explain generalization. And there's a lot of work trying to link
the double descent phenomena.
double descent and implicit regularization.
I think this can definitely explain the implicit regularization because we show that it have like explain why there's a low rank implicit bias because your weights are actually like here. So because you're only updating this kind of invariant matrices here, right? It's pretty low rank. And this rho is depending on your initialization, right? If your initialization is very small, this rho will be very small, and that's why the weight matrix is low rank.
So is it effectively under parameterized? Is that the point? No.
I think it's like neither overfit nor underfit. I think it's just this dimension of the subspace is proportional to the degree of freedom of your problem.
The law of parsimony hold when you are using SGD, not like.
That's a good question. I think so. I think if you do gradient, like not full batch, but not full gradient, but batch gradient, I think it also approximately holds.
So the experiment for nonlinear networks, you are doing gradient descent.
Yes, we are doing SGD, and there is you can still see the
The series using the whole batch.
Yes, right. And the theory actually is holding for gradient descent with weight decay. I think it also potentially holds with gradient descent with momentum. Yeah. Yes.
Slight follow-up question. So do you think this gradient descent with that initialization is finding a very good minimizer. I mean, you could imagine completely different optimization algorithms, especially for the deep linear network, like block coordinate descent, right? Update one matrix at a time. It's just the least squares kind of problem, right? And that would be a completely different algorithm. Do you think it would find maybe this is a two-part question?
Yeah, I think the implicit bias could change for different algorithms.
Yeah.
I think for this gradient descent type methods, this kind of low. For coordinates, I'm not exactly sure actually.
So it's kind of amazing that the simplest algorithm that, you know, people came up with first, backpropagation, has this apparently desirable implicit bias.
Right.
Remarkable.
Yes.
Do you think if the classification data set has some hierarchical information like image nets, they have like annual classes, beta classes, like big superclasses, right?
Yes. So there could be, if you just consider a superclass, there could be induced some low rank structures as well.
Do you think those low rank structures could convey those superclass information?
We haven't tried, but that's something I conjecture. But obviously for this small class like CFR10, MNIST, right? So you can see very strong low rank structures there. Yep. Yes.
So since you're basically just updating like a low rank version of the matrix, like why do you need a large matrix in the first place? Like does having the additional parameters help?
Yeah, that's a good question. Actually, we did some experiment, some like a backup slides, I think. Yeah, so if you compare the, I think that's a good question, right? So if you just take the matrix, deep matrix factorization, completion as the example. So you may wonder, right? So I mean, why not just to use like say, like that the intrinsic rank is to our like head, but to our head. Why not you just do a 2-layer Barrel-Montero to our head, but to our head matrix factorization and compare with this compressed network? And actually, compressed network is working more efficient than the narrow network. So here is an illustration, and this is we are increasing the x-axis is our head over parameterization or estimation of the rank, and the y-axis is the number of iterations. And you can see that the deep compressed network is converging faster than the narrow network. And if you compare the time, right, so the compressed network is also more efficient than the narrow network. I think the reason for this is because the y is actually doing some preconditioning of your algorithm and making your iteration, reduce your number of iterations, making your convergence faster. Yeah. Any other questions?
So you mentioned that number of ranks is approximately equal to the number of processes that come to the denominator in the experiment.
Yes, it's proportional to the number of classes.
So if the hypothesis is that it's doing matrix preconditioning, could you hypothetically use a preconditioning matrix?
But that could be kind of expensive. Preconditioning could be expensive.
Okay.
Yeah, somehow we are like using the y to implicit do that, and here doing compression will have achieve computation efficiency. Okay, so if no more questions, just end here. Thank you.
Also, I think this is something so big philosophy. Like we said, even you will assume there is some like yeah, this is your brain.
是啊，类似刚才找的筛子。现在这个变成 L。OK， 因为那个